then you have a set of all the bases of all those vectors that you have, so it's like a bunch of subsets. And so, so it satisfies two axioms. First of all, there are bases, and second of all, if you choose any two bases in this matroid, in any matroid, and you choose a subset of the first basis, you can find some subset of the second basis, so that when you switch the two subsets, you still have bases. And so this, this second axiom, it automatically makes it so that all the elements, all the bases, are of the same order, so we call this the rank of the matroid. And that's analogous to, say, like the dimension of the vector space. And so here's an example of a matroid. And so like if we consider these four vectors and we label them 1, 2, 3, 4, then our set is just these labels 1, 2, 3, and 4. And our set of bases are all the sets of order 3 that form bases. So 1, 2, 3, 1, 3, 4, 2, 3, 4. Okay, so back to the spaces exchange property. So it basically allows us to swap elements between two bases to potentially find bases that you didn't know were bases before. Like if you don't know the entire, like the full matroid basically. So you choose two bases. You can choose two bases in a subset of the first basis, but you're not guaranteed what the subset of the second basis is going to be that you can swap it with, other than it's going to be of the same order, because you want the resulting bases to be of the same order. So we refer to a choice of two bases and the subset of the first basis just generically as a 3-tuple, and the potential subsets of the second basis to swap it with as candidates. And so we're going to use this following notation. So this is just saying from the first basis, choose a subset and swap it with some subset of the second basis and form two new bases, or potentially bases that already exist, or that you already know exist. So here's an example of the basis exchange. So let's say you start with these three bases, and you choose this 3-tuple, so you choose basis 1, basis 2, and you choose A1 and A2 from the first basis. Then you want to see what you can swap it for in the second basis. So it's any subset of order 2, so these three. So you have to have 3 cases, 1 for each of those subsets. So case 1, you swap A1, A2 for B1, B2, and you get these two new bases. And so continuing with case 1, if you examine this another 3-tuple, basis 5, basis 3, basis 5 being this new basis that we just got, and we look at B3 from basis 5, and then we want to swap it for something in basis 3, then it's either C1, C2, or C3 from B. So then we have another 3 cases, case 1-1, 1-2, 1-3. So this generalized conjecture for matroids is what I've been working on. And so basically you have a matroid of rank n as opposed to a vector space of dimension n. And so you have n bases. You're given n bases in that matroid as opposed to n bases in a vector space. And so it just says there's n pairwise disjoint traversals of those bases that are bases. So if you think of each of the n given bases as having a color, we just call these pairwise disjoint traversals rainbow bases, and you want n of those. Okay, so Winnie Chan's approach to this generalized conjecture was to break down to 3 cases. Case 1, 2 members of the matroid are dependent. So that means that in vector space terms, you have 2 vectors pointing in the same direction. And so case 2, the joint of 2 elements of one base equal to that of another. So you can think of that as having 4 vectors, and 2 vectors span the same plane as 2 other vectors. And case 3, she proves a rather abstract, complicated lemma, and uses that to prove the conjecture. And so my approach is to forget about all these special cases and lemmas, and use only that basis exchange property that I introduced in the beginning. So if we start with the given n bases that the conjecture provides you, and then you have to sort of complete the matroid step by step, because those n bases don't make up the entire matroid. Like there's other bases that are implied by the spaces exchange property of matroids. So you go step by step and choose 3 tuples and branch off into cases and whatnot, and you keep finding new bases until either you have a full set of disjoint rainbow bases, so you've proven the conjecture for that case, or you complete the matroid. So that means you cannot infer any new bases. So that means that this matroid, or this set of bases, now satisfies the second axiom, and so you have a matroid that does not prove the conjecture, and so that would be a counterexample. Okay, so there's some issues with this approach, which is that, first of all, each time each time you want to make a swap, like each time you want to apply this basis exchange property, you have to choose from a number of subsets of the second basis. Because remember, you have two bases, a subset of the first basis, you want to swap for a subset of the second basis. And so there's multiple subsets of the second basis that you can choose from, and each one needs a new case. So you have to branch off in a lot of cases. And there's also a large number of matroids, even for n equals 3, and n equals 4 they don't even know because it's too large to compute. And also there can be a lot of 3 tuples you have to consider, because there can be a large number of bases and large number of non-trivial subsets of the first basis. Like if you choose the entire set or the empty set, then the basis exchange property will help you a lot. So first of all, we can eliminate some 3 tuples. So if the basis exchange property is already satisfied, then we can't infer any new bases. So like this is an example, basis 1 and basis 2, and you choose A1 from this first basis, then, well, there's already an A1 in the second basis, so all the basis exchange property says is you can swap these two A1s to get back the same bases. So that doesn't help you. And so in order to minimize the number of cases you have to consider, basically I compare the 3 tuples using the following criteria. First of all, you want less cases. So like the ones that you can eliminate as many candidates as possible. And if that's the same, then you prefer bases that are closer to being rainbow. So like a rainbow basis is just like a basis that has members from every single one of the n starting bases. So like let's say you have at least one member from like n minus 1 of the starting bases, and you're almost rainbow basically. So you want one that's as close to rainbow as possible, or just completely rainbow. And if that's still the same, you want the 3 tuples that give you bases that are most disjoint with the current set of rainbow bases that you know to exist. Okay, so in order to eliminate cases, first off, like in mathematical proof, you're often like, well, this case is similar to that case, so we only consider one of them. So I try to basically formalize this concept in the program. So basically, this is best explained by example. So if you have these 2 bases, and you choose A1 from the first basis, you can swap it for either B1 or B2 in the second basis, and you get these 2 sets of bases that result. So these first 2 are just B1 and B2, the first 2 bases. And then, but if you notice, if you swap B1 and B2, here, you get the same thing. Here, you get this. And here, you get this. So if, in that case, you only have to consider one of these cases and you eliminate the other. Okay, and superset cases, this can also best be explained by example. So if you let all these letters be bases, you can see, and this is basically like a case tree. So like, let's say, at first you get 7 bases, A through G. And then you find out that you have to branch off into 2 cases. In one case, you get bases H and I. In another case, you get bases J. And so let's say the program takes the step of going down the left side of the tree first. And after this case, say you've proven it. And so then you consider this case. Well, here you get this basis L that you had over here. So what you can do is you can just go over here and ignore the fact that you have these extra Mn and P bases and just follow this through. And same thing here. You have H and I from this case, and you already have HI up here, so you can just ignore all the other bases you have and follow this entire subtree that's been solved. And this is just an extreme example where you can do this for everything and solve or prove it. Okay, so, and if you prove the conjecture, then you can just eliminate those cases right off the bat. And if you eliminate all the cases for any 3 tuples, so if you find a 3 tuple where you eliminate all the cases, then that just means that you've proven the conjecture for that case. Okay, so the progress that's been made so far is the program can be run for any n, and it proves n equals 3 with only one case, as opposed to 1 each chance 3 cases, and it does it in like a very elementary way. And actually, yesterday, I made some pretty extreme changes to the program, and so I started running it yesterday, and this morning it was halfway done with n equals 4, so I think like within, I think like right now it could be done with n equals 4 possibly right now. I mean, it was halfway done when I left, so. Okay, so basically I proved this like much stronger version of the basis exchange property. So And that really, really reduced the number of cases. And so this is a significant result because n equals 3 is the only case that's been proven for all vector spaces. Because like all the other cases have been proven with Allen-Tarski conjecture, which doesn't imply all vector spaces. And it's also the only case that's been proven for the generalized matrix conjecture. So this would be, if it finishes, it would be the second case that's ever been proven. So the full proof for n equals 3. We have internet here, right?
Sure.
Okay, so this is output generated by the program. So I start by feeding it these 11 bases, and that I use the base exchange property computer does by hand. And so like here this means that you're swapping A2 and B7 for C2 and B6, and you eliminated A3 because it's in B7, so all it means is like B7 already has an A3 in it, so if you swapped it over, you have two A3s. And so you have two vectors that are the same, so that would not be a basis, so you eliminate that. And then minus C3, because if you swap C3 over, it would solve the conjecture. So it keeps doing this, and eventually it proves the conjecture, and it ends up with 38 bases and 12 rainbow bases. So that's the entire proof of n equals 3. All you do is apply the spaces exchange property over and over again.